Okay, so last time we were talking about numerical solutions, and we were talking about this specific problem here where we had a current lead. It was a one-dimensional steady-state problem. We went through the steps that we talked about, which were to distribute nodes. So we put our nodes, along the computational domain from 1 to n. We did a control volume around each node and an energy balance on that control volume. That gave us a bunch of energy equations, n of them, and then we approximated each term in those equations, which gave us a set of algebraic equations that we could solve in order to get an approximate solution to this problem, right? So these were the main outcome of what we did last time, was this set of n equations in our n unknowns. And we said that once we have these equations, solving them is sort of a matter of math, and there's different ways of doing it. The way that we did it last time was we just entered them into ease. So we took these equations, entered them in ease, and ease was able to solve them pretty easily. We said that's a good way to go for small problems, but as the problems get larger and more complicated, probably ease is not your best tool of choice. So we're going to move towards some techniques that you can use in more formal compiled programming languages, and therefore will be able to deal with much larger problems more computationally efficiently, right? So let's talk today about the second technique, which is matrix decomposition, right? So this is a set of linear equations. We said that if we want to put this into a matrix form like this, ax equal b, we have to remember our linear algebra. And our linear algebra tells us that this matrix A is filled with all of the coefficients that multiply these unknown temperatures, and this vector B is filled with all the constants associated with each of these equations. And more specifically, the entry in the A matrix that sits in the ith row and the jth column is nothing more than the coefficient in the ith equation here that multiplies the jth unknown, right? So ij, the first index corresponds to the equation, the second index j corresponds to the unknown, right? And then b is just the bi is just the constant associated with the ith equation. So if we keep this in mind, really all we need to do is be real clear in our own minds how we're going to order our unknowns in this vector of unknowns x, and how we're going to order our equations in a and b, right? And for this problem, there's not a whole lot of different choices, right? We're just going to put the temperatures in order in this vector x, and we're going to put the equations in order in a and b, right? So after that, it's kind of turn the crank. It makes it a little easier if you take each of these equations and rearrange them so it's very clear on the left side what coefficients multiply the unknowns, and on the right side what's the constant, right? So that's what I've done. Okay, so that's what I've done here. So let's see. The unknowns in this equation are T2 and T1, right? So if I go through here and let's just pick out these unknowns. So here's an unknown, here's an unknown, and here's an unknown, right? So those go on the left side of the equation. So I took the T1 stuff, and this is then the coefficient that's multiplying T1. And I took the T2 stuff. This is the coefficient that's multiplying T2, right? And then everything else goes on the right side of the equation. So that's this stuff and this stuff, and that becomes my constant, right? So with this, then it becomes pretty easy to put these coefficients and constants into the right place in A and B, right? So we're dealing with equation 1, so everything is going to go in row 1 of A and row 1 of B, so that's pretty easy. And then all I have to do is put it in the right column. So this is the coefficient multiplying my first unknown, so it'll go in the first column. So this is then going to be A11. This is the coefficient multiplying the second unknown, so it'll go in the second column. So this will be the coefficient A12, right? And of course this is then B1. And that's all you have to do as you go through everything, right? So the next thing we would do is all of our internal nodes. So I have 3 unknowns in this equation, right? I have ti minus 1, ti, and ti plus 1. All I'm doing is pulling those parts of the equation out and putting them on the left side, so it's very clear what multiplies those unknowns, and then whatever's left over, which is this thing, goes on the right side. So ti is multiplied by, it looks like from here I get a minus k ac over delta x, and from here I get another one, so that's what this is. Ti minus 1 here, and ti plus 1 here. And it becomes easy then to put this into the right place in A and B again. So I'm talking here about my ith equation, right? So everything here is going to go in row I, and then it's just a matter of putting it in the right column. So this is the ith unknown, right? So this is going to go in row I, column I. This is the I minus 1 unknown, so this is going to go in row I, column I minus 1. This is the I plus 1 unknown, so this will go in row I, column I plus 1. Right? And then this is B sub I. And the same thing for this last equation here. So that's, oops, that's not what I wanted to do. So that's what I needed to do, and at this point it's pretty easy to construct A and B. Once I construct A and B, right, so the matrix A and the vector B, I'm just solving, well, let's go back here. I'm just solving this equation here, this matrix equation. The way I do that is I multiply both sides by the inverse of the matrix A. So A inverse times A is the identity matrix. So here I just get X, and I'm left over here with A minus 1. So the inverse of A times B. And that's actually, we'll see, not the most efficient way of doing this to actually build the inverse of A. It's much easier to just decompose A. But Matlab has techniques for doing that very easily, and almost any software that you care to pick up will have some method of doing this because it's just so common. So let's go look at what this looks like in Matlab. So let's see if I can find Matlab. I have about 20 windows open here. So okay, here's Matlab. This is my Matlab code. So if we just go through this, let's see, what have I done here? These are all the inputs, right? There's the cross-sectional area. Here's distributing the nodes, right? So, if I look at what this looked like in ease, this was a duplicate loop. In Matlab, it's a little bit different in terms of the, the protocol. In any language you want to pick up, it's going to be a little bit different. You're going to have to know how to program for loops or duplicate loops. Here it's a for loop, right? So I have 101 nodes. So for I equals 1 to n, this is the position of every node, right? And it's pretty easy. This actually is not a very efficient way of doing this in Matlab. Matlab's really good at solving equations if you vectorize them, but it's a little beyond the scope of what we're going to talk about here. Here I'm just setting up A and B now. So A is a big matrix, right? It's got n rows because there's n equations. It's got n columns because there's n unknowns, so it's n by n. For a finite difference type solution like I have here, the best way to do this is you just set it up as zeros everywhere, and then as we go through each of these equations, we will just turn zeros into non-zeros as necessary, right? So if I go through, where's my keyboard here? So if I go through the equations that I derived, so here, this first equation right here, right? This is A11, A12. So those are the only two non-zero elements in row 1, and then this is B1. Right? So that ought to be exactly what I've done here. A11 is that. Right? It's the coefficient multiplying T1 in equation 1. A12 is this, the coefficient multiplying T2 in equation 1. And then this is the constant. Right? Same thing for all the internal nodes. And then node n. And then at the end, it's just a matter of taking the inverse of A and multiplying it by B. So let's run this, and I'll bring the plot over. So here's the plot. It's the same thing we got in ease because it's the same solution. I did say that building the inverse of A like this is not very efficient, right? So if I were to go up to something like, I don't know, let's make this 5001 and run this again, you're going to see that it takes some time, right? So it's thinking right now. Now it's done thinking. If I go look at the solution, actually I think it's still thinking there. If I go to look at the solution, now there's many more nodes, but that took a long time, right? So one way I can make this a little faster is to not build the inverse explicitly, but use this / command here. So this / command is the same as this command here, but it's not actually building the inverse, it's decomposing A, right? So if I run this now with the same number of nodes, what you should see is it's substantially faster, right? So now it's done. Same answer, just a much more efficient way of doing it if I don't need that inverse. The other thing that we should point out is that A is pretty sparse, right? I mean, if you look at each row of A, there are, so at this point, I guess, 5,001 elements in each row of A, but only 2 or 3 of those are not 0, right? So all the other ones are 0. So most of A is filled with zeros. And if you have that kind of a situation, which you often do in conduction problems, you have what's called a very sparse matrix. And there's methods of dealing with sparse matrices that are much faster than dealing with full matrices, right? There's a little more overhead in setting up those kind of methods, but Matlab makes it really easy to deal with sparse matrices. So you got to figure out how to do that. Basically, what you do in Matlab if you want to use sparse matrix operations is you just declare A, instead of being a full matrix, right, you declare it as being a sparse matrix. And you do that with the spalloc command here. So here in my Matlab code, where is it? Right here. This was saying A is equal to a full matrix and it's just a bunch of zeros, and I'll change the zeros as needed, right? If instead of doing that, I use the spalloc command like I've done here, it's telling MATLAB, oh, A is now a sparse matrix, right? So it won't be completely full of entries. We're going to ask you actually to keep track of those entries that aren't 0, and you don't have to keep track of the zeros because everything that isn't explicitly assigned, it's going to be a 0, right? So again, this is all behind the scenes. You don't have to worry about it because those kind of procedures and methods have been already dealt with for you, and this is how you do this in MATLAB. So if I want to allocate A as being a sparse matrix, I use the spalloc command. The spalloc command takes in 1, 2, 3 arguments. The first 2 arguments are just what's the dimension of A, right? So A is n by n. This first argument is going to be n, right? There's n equations, so there's n rows. The second argument is also going to be n. There's n columns because there's n unknowns. This third argument, though, is pretty important, and it's saying, you know, how many non-zero elements are there going to be in A at most, right? So how much memory do I have to allocate towards A? And if you look at these equations here, you know, okay, there's n of these equations. In the first equation and the last equation, there's only 2 non-zero elements. In every other equation, there's 3, right? So, you know, at most, there will be 3 times n non-zero elements. In fact, that's too many, but that's okay. We're a little too big. So that's 3 times n right here. Right? So now I'm using sparse matrices, right? I don't have to do anything else. It just knows to use sparse matrices. If I run now, you can see it's blisteringly fast. It was done almost before I, you know, clicked. I can make this even bigger, so 10,000. It's still going to be really fast, right? So if you were to go to ease and ask it to do the same thing with 10,000 entries, I think you probably would actually exceed the number of variables you're allowed to have in ease. So it's just, this is a much better tool for doing large numerical simulations than ease is, right? Yeah, okay, and you know, when you get done, obviously, I hope it's obvious anyway, that the answer hasn't changed, right? It's just gotten better and better as I added more nodes. Okay, so that's matrix decomposition.